Hello everyone. Today I will introduce some relevant information about power mode for BLE-SoC. Today, I will guide you through a detailed introduction to power modes. We will primarily cover different low power modes, power management, and the application of low power modes. After this, you'll gain an understanding of the basic development process of power management and become familiar with the application of low power modes. Our goal is to offer you practical assistance. The power mode architecture comprises a platform module and a Bluetooth module. Platform power modes include active, deep low power state, and power down, while Bluetooth power modes include active and deep sleep mode. When Bluetooth is in active mode, the platform must also be in active mode. When Bluetooth is in DSM mode, the platform can be in any power mode. The platform module is responsible for managing the CPU, RAM, peripherals, clocks, and other components. Depending on the current platform power mode, it will place the components into the appropriate power-saving state. Platform power mode primarily consists of the following three modes. Active, all modules are powered on. It can operate in the following two submodes. CPU active mode offers ultra performance with a high-speed clock, resulting in relatively high power consumption. CPU sleep mode. The CPU enters sleep mode with the clock automatically slowing down to reduce power consumption, while allowing interrupts to wake up the CPU quickly. DLPS, deep low power state, offers lower power consumption with relatively fast entry and exit times, while maintaining RAM content. In DLPS mode, the CPU is inactive as the high-speed 40 MHz clock and PLL are powered off. However, the PAD, LPC, and RTC are powered on, enabling them to wake up the system. Power down. This is the ultimate low power mode with a relatively long exit time, during which RAM contents are not retained. In power down mode, both RAM and low-speed 32 kHz clock are powered off. The PAD and LPC remain powered on, allowing them to wake up the system. The following table provides details on the power state of components in different platform power modes and includes the average power consumption for each mode. The Bluetooth module is responsible for managing the Bluetooth MAC component. Depending on the current Bluetooth power mode, it will transition components to the appropriate power-saving state. Bluetooth power mode primarily consists of the following two modes. Active. In Bluetooth MAC active mode, the Bluetooth MAC can operate normally and allows interrupts and tasks to handle Bluetooth events. The relevant MAC registers are accessible, and the Bluetooth MAC operates with a 10 MHz clock source. DSM, deep sleep mode. In Bluetooth MAC deep sleep mode, the Bluetooth MAC ceases operation and enters a low power state. MAC registers are not accessible in this mode, and the Bluetooth MAC operates with a 32 kHz clock source. Note: the Bluetooth MAC module can only enter and exit DSM when the platform module is in active mode. The following content provides a detailed introduction to power management. To reduce system power consumption, unused modules can be powered off. When an event requires processing, the relevant modules will be powered on, allowing the system to respond to wake-up events. Different power management units exist at various system levels, each responsible for implementing power stage functions. In the Power Manager architecture, the Power Manager traverses each power unit sequentially by level, first the Bluetooth unit, followed by the platform unit. Within each power management unit, users can register callback functions for different power management stages, such as check, enter, and exit. During the operation of each power unit, the system will enter a low power mode when the entry conditions are met, and it will exit low power mode upon the occurrence of a wake-up event. The process for entering low power mode is outlined as follows. The system enters the idle task and no interrupts happen. In Bluetooth unit flow, If the check callback function returns true, the Bluetooth unit enters DSM and proceeds to check the platform unit. If the check callback function returns false, the Bluetooth unit remains active, with the platform unit entering CPU sleep mode. In platform unit flow, if the check callback function returns true, the platform unit will enter DLPS or power down mode, depending on the platform power mode. If the check callback function returns false, the platform unit will enter CPU sleep mode. The conditions for the system to enter low power mode are as follows. The system will enter low power mode only when all of the following conditions are met simultaneously. First, the system is executing the idle task, with all other tasks in a blocked or suspended state, and no interruptions are occurring. Second, the Bluetooth MAC module permits entry into DSM. There is a minimum sleep interval requirement in both non-link and link modes for Bluetooth. For RTL87X2C and RTL87X2D, the minimum sleep interval required to enter sleep mode is 15 milliseconds. For RTL87X2E, RTL87x2G, and RTL87X2H, the minimum sleep interval can be 7.5 milliseconds. Third, the platform module allows entry into low power mode. This requires meeting two conditions. The wake-up time period must be within acceptable limits. Generally, it should be larger than 1 OS tick, and the check callback function must return a pass value. The conditions for Bluetooth to enter DSM, deep sleep mode, are as follows. When in standby state, Bluetooth will enter DSM and will not wake from it. When in advertising state, if the advertising type is direct advertising, high-duty cycle, do not allow entry into DSM. If the advertising type is connectable or non-connectable and the advertising interval is greater than or equal to 15 milliseconds, entry into DSM is allowed. When in scanning state, if scan interval minus scan window times 0.625 greater than or equal to 15 millisecond, entry into DSM is allowed. Otherwise, entry into DSM is not allowed. In link mode, for master role, if the connection interval times 1.25 greater than or equal to 15 millisecond, entry into DSM is allowed. For slave role, if the connection interval times 1 plus slave latency times 1.25 greater than or equal to 15 millisecond, entry into DSM is allowed. In multi-link mode, when a device is simultaneously advertising and connecting, the interval between the current time and the next event must be greater than 15 milliseconds to allow entry into DSM. The conditions for the platform to enter low power mode are as follows. To enter into DLPS mode, after the execution of the check callback registered by peripheral and app, all check functions return pass. The period of the software timer or the time for task delay must be greater than or equal to 20 milliseconds. To enter into power down mode, all check callback functions registered by peripheral and app must return pass following their execution. Timed wake-up events must not be present. Note: if the Bluetooth module is allowed to enter DSM but the platform module is not allowed to enter DLPS, then the Bluetooth module will enter DSM while the platform module remains active. If the Bluetooth module is not allowed to enter DSM, the entire system will remain active. The low power mode exit process is shown as the right figure. Active wake-up events. These are events capable of directly waking up the system. They include PAD, LPC, user RTC events. These events have the ability to wake up the platform and trigger interrupts. Passive wake-up events. These events cannot directly wake up the system. Instead, they rely on the platform RTC to wake up the platform. These events include OS and BT events. Additionally, a Bluetooth interrupt will be triggered to wake up the Bluetooth module from DSM, deep sleep mode. The conditions for exiting from low power mode are shown as follows. Active wake-up events include the following events. 1. Pad wake-up with debounce, pad with high or low level, longer than debounce time, wake system. 2. Pad wake-up without debounce, pad with high or low level wake system. 3. LPC wake-up, higher or lower voltage than threshold trigger wake-up. 4. RTC wake-up, RTC interrupt can wake up system. Passive wake-up events include the following events. 1. OS event, OS timer and task delay can wake up system. 2. Bluetooth event, advertising, scanning and connection anchor arrives. After the occurrence of the above wake-up events, the system will exit from low power mode. It is necessary to ensure that related events are successfully configured before entering low power mode. In DLPS mode, PAD, LPC, RTC, OS, Bluetooth events can wake up system. In power down mode, only PAD, without debounce, and LPC events can wake up system. Application of low power mode. Power management is a modular and extensible framework. Users can register callback functions at stages such as check, enter and exit, to facilitate unified management during application startup. Application of low power mode. Users only need to perform corresponding configurations based on the application scenarios they wish to use. 1. Low power mode selection. 2. Register callback function. 3. Wake up event configuration. Users can get some debug info to find the cause of the following exception case. 1. Unable to enter DLPS. 2. Unable to exit DLPS. 3. Abnormal DLPS exit. Finally, we provide an application example to help users utilize it more effectively. Before adding support for low power mode in the application, users need to perform the following configurations. Register callback function. The user can register callback functions in check, enter and exit stage. Low power mode selection. The user can select the appropriate power mode according to their needs. The image on the right is an example where the enter and exit callback functions are empty, and the check callback function returns pass. In the Power Manager init function, users register the above callback functions and then set the appropriate power mode for BT and platform. Wake-up event configuration. Before entering low power mode, the user needs to configure the wake-up event. The table below provides the demo project paths and corresponding configuration details based on the 87x2 GIC for different wake-up sources. In active wake-up events. 1. Pad wake-up. The user can enable pad wake-up by configuring the GPIO enable macro to 1 and enabling or disabling debounce. 2. LPC wake-up. The user can enable LPC wake-up by configuring the LPC enable macro to 1. 3. User RTC wake-up. The user can enable user RTC wake-up by configuring the RTC enable macro to 1. In passive wake-up events. 1. OS events include task delay and OS timer. The user can create a task with a time delay or create and start OS timer to enable OS wake-up event. 2. BT events include advertise, connect, and scan. The user can start advertising, create a connection, and start scanning to enable BT wake-up events. Some common exception analyses are shown below. Unable to enter DLPS. The user can check the error reason to determine which component is preventing entry into low power mode. Unable to exit DLPS. The user needs to check if any wake source is set or if there are excessively long delay operations or OS operations within the DLPS enter callback. Abnormal DLPS exit. Users can check the wake reason to determine which source has woken up the system. This is an application example that configures a pad wake-up event without debounce. 1. Register a check callback function, which returns pass to allow entry into DLPS. 2. Register an enter callback function. which enables P3_2 low polarity wake up. 3. Register and exit callback function, which restores the pad configuration. 4. Select the low power mode for BT and the platform. Set the BT power mode to DSM and the platform power mode to DLPS. Thank you all for listening to my presentation on Power Mode Introduction. I hope the content was helpful to you. If there is anything unclear, please feel free to ask me questions.